This lecture is about an introduction to operating systems. So what is an operating system? An operating system is a middleware between user programs and hardware. For example, users use a computer to run various programs like a browser, an email client, and so on. And these programs run on the underlying hardware of the machine. For example, you can have CPU, you can have main memory or RAM, you can have a disk, you can have various other input-output devices. And programs run on this hardware. And what is an operating system? An operating system is something that sits in the middle and manages all of this hardware for the user programs. So before we understand what an operating system is, let's just see what happens when you run a user program, right? So some background first. So when you write a program, say a C program, what happens? A compiler translates the program into an executable. Say when you compile, you get an A.out on the disk, right? So next, what does this executable contain? This executable contains instructions that the CPU can understand, right? It has instructions and it has data, the variables that you've created in the program. And these instructions, note that they're specific to the underlying CPU hardware. So every CPU has a certain instruction set architecture, a set of instructions that it can implement, that it can execute. And the compiler translates a program into these instructions that can execute on the particular CPU. Right? And in addition to the hardware to execute instructions, the CPU also has a few registers. So what do these registers do? For example, there is one register called the program counter or the PC. What does it do? It points to the current instruction being executed. And there are a few other registers to store operands of the current operation being made, right? So the executable contains all of this. When you compile a program, the executable contains the instructions and the data of the program. So what happens when you run a program? To first run a program, there is the memory of the program that is there in the RAM, right? This memory has things like the code of the program, some data of the program, and so on. Okay, and the CPU has a set of registers. For example, it has the program counter that points to some part of the code, and it also has various other registers. So when you run a program, the CPU points the program counter to a certain piece of code, fetches that instruction from the memory. It loads any other variables, any other operands that this instruction needs. It performs some computation and then it stores back the result of the computation back into memory, right? So an execution of the program has this back and forth between CPU and memory, where the CPU is fetching instructions, executing them, and storing back results into memory. And the CPU also has an instruction cache and a data cache, right, where it stores the most recently used instructions and data, right? But we don't have to worry about this for now. So this is the background of what happens when a program runs. Okay, so now where does the operating system fit into all of this? So what does an operating system do when you're executing a program? So the operating system does several things, right? So the first thing it does is it manages the program memory. So you have your program executable, your A.out on disk, and the operating system fetches this executable into memory. So you have your main memory, the operating system copies this A.out into memory, okay? And the next thing it does is it manages the CPU. So the CPU has the program counter and various registers. So the operating system sets correct values to all of these things so that the program counter is pointing to the instruction to run and so on. right? So it sets up the CPU for execution. It sets up the memory with the program. It sets up the CPU for execution. And it also helps you communicate with all of these devices like the disk and various other input-output devices. All of these are also managed by the operating system. So let's understand each of these things in detail, right? So we've seen that the operating system manages the CPU, the memory, and the disk. So let's understand this in a little bit more detail. So what does it mean for the operating system to manage the CPU? So the operating system provides what is called a process abstraction. That is, what is a process? A process is nothing but a running program. You have a program on disk, an A.out, and when you run it, it becomes a process. So the OS creates and manages these processes so that you can run your programs on a computer system. And each process has the illusion of having the complete CPU to itself. Note that at any point of time, there's not just one process on the CPU. There are many different processes running. You could be listening to music while browsing the web, right? So all of these processes think they're executing on the CPU by themselves. And the OS gives them that illusion, right? So the operating system, we call this as the operating system virtualizes the CPU. Okay? And it time shares the CPU between the multiple processes. And it also enables coordination between all of these processes. So if you have multiple processes, all of which are, process P1, P2, P3, all of which are running on the CPU, the OS time shares the CPU between these processes, where each process thinks it is running alone on the CPU. And it also enables, if the processes want to talk to each other, want to exchange some data, any sort of coordination between these processes is also enabled by the CPU. So next, the operating system manages memory, right? So every process needs some amount of memory. So what does the memory of a process contain? The memory of the process contains many things, right? So there is the code, there is the the instructions that the user has written which have been compiled. Then there is the data, all the variables that the user has created. Then there are also something like the stack and the heap. We'll come to these later, but at a high level, a stack is where when a program makes function calls and it has to store things like arguments to the function or return address from the function, that is stored on the stack. And when you malloc, when you allocate memory, that gets stored on the heap. So the memory of a process has all of these things, and the operating system manages all of this thing. That is, each process doesn't have to worry about where all of this memory is placed in the actual hardware. Every process thinks it has the entire memory to itself, and it gives addresses to the code, data, everything, all the parts of its memory starting from 0, and it addresses this location, that location using a certain address that we call the virtual address. But in fact, all of this memory image could be placed in the memory in different pieces. For example, the code could be here, the data could be here, the stack could be here, the heap could be here. It could all be in different places in the actual physical RAM, and the RAM could be shared amongst multiple processes. However, each process is not aware of all of those details. It just thinks I have some amount of memory starting from byte 0 to byte whatever, 4 GB. That's all a process thinks. And the OS actually takes care of placing all of this memory into the actual hardware. And when the process says, I want memory at a certain location, at a certain virtual address, it will actually translate it to the actual physical addresses and fetch the piece of memory. Right? So in some sense, the OS virtualizes the memory as well. It gives each process the illusion that it has a large amount of memory available for itself, so that a process does not have to worry about the nitty-gritties of where its memory is placed in the actual physical hardware, right? So the first thing we've seen is OS manages the CPU on behalf of the process. Next is it manages the memory on behalf of the process. And finally, it also takes care of talking to all the other devices like the disk, the network card, and keyboard and mouse, and whatever other device you connect to your system. The OS has code to talk to all of these devices. So the OS has what are called device drivers. What is a device driver? It is a piece of the operating system kernel code that talks the language of the hardware devices. So every hardware has a certain different language in which it communicates, right? And a device driver understands that language. It knows how to issue instructions to devices. For example, you want to tell a device, hey, get me this file. The device driver knows how to talk to the device. And it also knows how to respond to events from the devices. For example, when you press a key on the keyboard talks to the device driver and the device driver understands what key you've pressed, right? So all of this functionality is there within the operating system, so that anybody writing a program does not have to really worry about how do I talk the language of this particular device. And finally, the operating system also manages a file system, right, where data that you want to store persistently. So whatever you store in the RAM is lost after a reboot, but whatever you store on a file system on the disk stays forever, at least as long as the disk is up and running, right? So the operating system manages all of these devices for you. So now we have a basic idea of what an operating system is supposed to do. Let's kind of see what are the things that people keep in mind when designing an operating system. What are the design goals? Of course, the first and foremost goal is convenience, right? Why do we use an operating system, and why not just directly run our programs on the hardware? Because it's just immensely convenient to use an operating system, because it abstracts out all the details of the hardware. So convenience, abstraction of hardware, this is like the primary goal of an operating system. Okay, and in addition to these, there are also a few other goals. For example, efficiency is another goal in the design of an operating system. So when you are running processes on a CPU, the OS tries to make sure that the CPU is efficiently utilized. When it is storing the memory of processes in the physical RAM, it makes sure that not a lot of space is wasted, right? So it aims for efficiency. And finally, another big thing is isolation. When you have multiple processes running, they are protected from each other. So one process, one user's program cannot go and destroy the memory of another user's program, right? There's a lot of protection, isolation, security built into the operating system. So these are the goals that any good operating system usually meets. So we are almost at the end of this introduction. We'll end with just a brief history of operating systems. Right? So initially operating systems just started out as a library, right? A set of functions that conveniently abstract out the hardware that can be reused across different programs to provide all of this common functionality of accessing devices and so on. So it started out as a library, right? So later, invoking operating system functions in the library, it was just, you're making a function call, a procedure call. But later on, it moved to something called a system call. Right? So today when you want to invoke OS services, you make what is called a system call. So what is a system call? A system call is slightly different from a function call. We're going to study about this later. But the OS code, when you run the OS code in today's operating systems, it runs with a higher privilege level. That is, there's a certain amount of protection built in. Your user program cannot do a bunch of things like access devices, whereas the operating system has more privileges, and when you run OS code, it runs at a higher privilege level. And this really gives you the security and isolation properties that an operating system provides. Right? So initially an OS was just a bunch of functions bundled into a library, and later on it has evolved into something that runs with more privileges, that tries to provide isolation and security. Okay, and it also evolved from running just one single program. The old mainframe computers would just run one program at a time, to today your laptops, your desktops, and even your phones run multiple different processes at the same time. Multiple processes execute concurrently, right? So operating systems have added more features and have gotten more complex, and today they are an integral part of using any computer system. Right? Nobody no longer just directly runs their code on the hardware. They always go via an operating system because it is very convenient. So that is the end of our first lecture on the introduction to operating systems.